We begin with Module 5, Message Passing Graph Neural Networks, okay, MPNNs, basically deep learning over graphs. Let me start with a one-slider. We've seen how to apply feature generation, engineering on graphs, basically capturing different structural patterns like triangles and so on from the graph. Okay, we also saw how to apply node embedding or how to learn embeddings, node representations on graphs, okay, from the graph content. GNNs basically apply the deep learning approach where you do not include engineered features, you do not engineer features, but rather let the model understand these features automatically. Okay, and here we are basically maintaining the embedding the representation of the nodes as part of the model. We're computing it as part of the model. And in the case of graph, we update the embedding of the node repeatedly by consulting the neighbors, by looking at the embeddings of the neighbors. Now, we do it repeatedly. Okay, we apply multiple rounds of this message passing approach, which means that we basically look at patterns not just in the immediate neighborhood, but rather in the larger neighborhood. Okay, capturing patterns, not just edges. Okay, now all the computations are differentiable, and therefore we can train the parameters of the model based on a task. Okay, based on the machine learning task that we want to solve using gradient-based learning, like Adam Optimizer or SGD and so on. Okay, but we will see that graphs come with some special challenges. You don't see in vanilla machine learning over matrices, over tables. And basically, the idea is, the question is how to scale such a computation. Because it may be the case that the entire graph is connected, and to compute the embeddings, you need the full graph. So there's no natural notion of mini batching, okay, of a batch. Okay, so we need to build these ideas of mini batching into the model. We're going to look at that. And also some challenges that arise from the fact that you're collecting information by several hops from far nodes, or by the fact that you're aggregating possibly many nodes, many neighbors in your functions. So that's over smoothing and over squashing. We are going to discuss these challenges that are unique to graphs. Okay, so what are the goals of the module? So we'll start by understanding the general structure, general anatomy of message passing GNNs. Okay, we'll do an analysis, basically get an intuition about what you can express with MPNNs, message passing GNNs, by using the Weisfeld-Lehmann isomorphism test. We'll draw a connection between the two. Okay. Now we look at some of the more popular GNN architectures. We will learn how they incorporate heterogeneity, which is very important when you want to apply GNNs to relational machine learning. Okay, so we'll see how we're doing that. Okay, we will understand some of the challenges of learning GNNs, learning and applying GNNs on graphs, specifically on large graphs. We're going to look at techniques for mini batching of GNNs. Okay, and we're going to dive a little into the task of link prediction, which is a major scalability challenge, because if you want to predict whether there's going to be a link between two nodes, you essentially need to look at every pair of nodes. So we'll see how to do it effectively using a deep learning approach. Okay, specifically, this module has three parts. We'll start with homogeneous GNNs, basically understanding um, the idea in standard MPNNs, talking about expressiveness and the Weisfeld element. Uh, and then the next part is going to look at the heterogeneous MPNNs, basically how we adapt the homogeneous MPNNs to the heterogeneous case. We'll talk about uh, incorporating directions of edges, labels, and so on. We'll look at some specific heterogeneous architectures. And then we're going to look at some pragmatic aspects, specifically these learning anomalies that you have on graphs, mini batching, and then link prediction.